Vidalin from Seqens. He will talk about optimization of the lipase B for specificity of substrate selectivity of a transesterification reaction. Olivier, you have the floor.
Hi, everyone. Thank you for inviting me for this conference. Today, we'll present to you a case study where we use the different tools we have developed at Protéus to optimize, in that specific case, a lipase for its specificity on substrate and selectivity toward this transesterification reaction. Briefly, I will give you a quick glance at the company. In fact, Protéus is part of a bigger group called Seqens. Seqens is an integrated global group in pharmaceutical for synthesis of specialty ingredients. It's a worldwide group with 24 sites and 3 research centers with 300 people working in it. Overall, it's about 3,000 people. And 70% of the work is done for pharmaceutical synthesis, CDMO, proprietary APIs, or specialty ingredient like cosmetic, fragrance. Protéus exists since quite a while now, since 1998, and has been bought in recently, or acquired recently by Seqens. It's focusing on tailoring enzyme and biocatalytic process. It's a small team of 25 people based in Nimes, south of France. We do have a collection of microorganisms, proprietary one, and access to a specific collection like 6,000 different microorganisms. We do have some proprietary tools for directed evolution, and the aim of the company is to identify an enzyme, either native or enzyme that we want to evolve for a specific process, and develop all the process from production of the enzyme toward the final product through some plant site belonging to Seqens. And for that, we have developed several tools, and what platform that has been developed is the Sequenzyme platform. Sequenzyme platform, it's 4 different steps. The first step will be Sequenzyme kits, which are kits of different enzymes that has been isolated, characterized, directly available from the shelf. And if you need some specific enzyme, we use a Sequenzyme Explorer, which is allow us to pick into our diversity of genomic database, proprietary database, or microorganism to find some new native enzymes or some specific enzyme for the reaction we want to catalyze. And when the enzymes are not optimized, we use our Sequenzyme Builder with directed evolution, L-shuffling, or other semi-rational methods to improve the biocatalysts. And finally, we can deliver the final product either as an enzyme or a full biocatalytic process going from the enzyme up to the final product. So just briefly to comment on the Sequenzyme kit, you can find kits available with covering 7 different enzyme families. And in each family, you will find a panel of different enzymes. And briefly, if you take, for instance, the transaminase, you could find enzyme with different conversion rate, different enantiomer selectivity. And that could be a good start to start the screening. So either we can start the screening for a project starting with the kits. And a good example is this one, where starting from the kit, we identify an aldolase that has been used to transform some glycine, a very small amino acid, into diserine. And now this process is industrial. And in fact, with a very, very high specificity at 99.9%, high productivity, and it only takes fermentation, 15 cubic meter fermentation scale to be able to produce tons of diserine with an enzyme load very light, something like 5% weight to weight. And when I speak of enzyme, in that case, it's more whole cell extract, so it's even easier to produce. and the impact of the enzyme on the final product is 6%. So you see, when we want to develop a biocatalytic process, we can start from these kits already of enzyme well identified on the shelf, and move forward toward something more specific. And that's bring me to the case of the lipase B, where we wanted to identify a new lipase with a specific specificity for the substrate, and a very selective reaction toward the alcohol group we wanted to be reacted. So we started from an existing reaction that were identified with a substrate, an alcohol with 3 alcohol groups, 2 primary and secondary. And we knew this reaction was successfully catalyzed by a novozyme 435. But this enzyme needs to be immobilized to perform in the right conditions. What we wanted to do was to identify a new enzyme able to specifically recognize only, catalyze the reaction on only 1 primary alcohol, and also able to avoid some contaminants present in the substrate solution. And in the original solution, in the original reaction, in fact, the novozyme 435 was working very well in terms of conversion, but over time, the reaction was providing some non-specific reaction, and also was not very specific regarding the impurity. So that was a challenge for us to find a high specificity for the alcohol group that we wanted to target, as well as a high specificity for the substrate, and cherry on the cake, increase the conversion rate. So that's a reaction we started from with a novozyme 435. So the standard was quite high in terms of conversion. However, if you look at the non-specific product over time, this enzyme was catalyzing the wrong reaction and bringing over 24 hours more than 10% of the non-specific product. And more than that, the reaction was reversible, and the enzyme was degrading the substrate we provided in the first place. And when we, in that specific picture you couldn't see, but if you look more specifically on the ratio on the targeted compound and another non-specific compound, not the one from the alcohol, but the one present in the substrate solution, we could see that over time there is a decrease in appearance of this non-specific compound, and in this kind of assay was not sensitive enough to perform a high throughput screening and discriminate for all these parameters. So what we wanted to do was to evaluate the feasibility of developing a high throughput screening and to be able to screen thousands of mutants. The optimal conversion reaction was performed with an immobilized enzyme, and that was not compatible with high throughput screening. So that was a first hurdle we had to go through. Also, the assay needed to be miniaturized and to be sensitive enough to discriminate between the different components and the different reactions that were taking place in it. Once that will be the first step of our work, we spent quite a lot of work trying to identify what was the good condition of the assay to be able to have a very robust high throughput screening. And that was, I guess, the key on this project. Once that's been performed, we started, of course, from one identified enzyme that we had on our proprietary collection, evolve it to improve the performances, and start to use the high throughput assay to screen them. So to develop the assay, besides the fact the first enzyme was immobilized, the components that were taking place were not compatible with the throughput screening. The conditions were not right. So we had to simplify the thing. And first of all, we had to find a better acid donor to improve the sensitivity and quality of the reaction. For that, the vinyl ester was the best candidate. And to mimic the alcohol with a primary alcohol we wanted to target, and another alcohol that was more hindered compared to the other one, we used 2 different alcohols. We split the alcohol in 2. We use 1 butanol as the simple alcohol with the primary group we wanted to target, and isobutanol to mimic the inner primary alcohol group. Once that has been done, we tested it in normal scale with all the compounds and the original enzyme, the Novozyme 435, also compare with our candidate enzyme. And what we found that this test was giving us a high rate of conversion. It was very sensitive for the non-specific compound. As you can see, we can see very quickly appearance of non-specific reactions. It was validated with enzymes that were not immobilized, and also it was scaled down to microtiter plates. So we had our high throughput test, and we were able to start the next step of the program, which was the screening of diversity. So as I say, we started for a well-identified enzyme, and the next step was to improve this enzyme. In fact, our candidate enzyme was having a conversion rate pretty low compared to the Novozyme 435. It was 33%. However, we did not detect any non-specific product generated in the assay we just developed, compared to the Novozyme that was giving in a normal assay more than 13% of non-specific product. The next step was to develop a library of mutants, and for that we use EvoCyte technology, which use prone error PCR, where we generated a series of mutants and giving us a diversity of enzymes that we tested for the best variants. And earlier, we heard about the fitness of the enzyme and how we wanted to make sure that the enzyme are still able to work whatever the number of mutation we put in it. And we pay a great attention to that by calculating the optimal mutation load, which gives us basically the number of mutation we can put into the gene, a specific gene we want to target. So we increase the rate of mutant on each gene, and we evaluate rapidly what could be the capacity of the gene to stop working and to give us some non-functional enzyme. And that is to maintain at the end a library with a maximum of enzymes that are working and with a sufficient quality to be screened. And that's what you can see on the right. You can see this this mutation rate. When it's very low, you can see the activity of the enzyme that is still performing, which is still high. The frequency of enzyme working is still high. And as soon you start to kick a high number of mutation, the efficiency of enzyme is going down. So you can see the number of mutant you generated that not working anymore. And for this one, the ratio was about 3.6. So we decided to go for a library containing an average of 4 mutation per gene at the maximum. So we generate a library of 14,500 mutants with an average of 1 to 4 mutants per gene. And we screen them using the new throughput assay for conversion rate, anything that was above 5%. For the alcohol specificity, as I mentioned, we wanted the primary alcohol, the less injured, and also substrate specificity, where we put some the substrate of interest and some contaminants. And what we found is for conversion rate, we found quite a lot of mutants with having an improved conversion, and 157 that were having improved performances above the Novozyme 435. And for the alcohol group specificity, we found less mutants that was having the alcohol specificity, but also we found 5 of them that were having alcohol specificity, but that was impacting the conversion rate. So mutations are not really independent, and unfortunately, sometimes we cannot have everything in one go. So that might necessary. We might need to perform several rounds of mutagenesis. And finally, the third group of mutants, we identified 12 of them that were having a very high substrate specificity, and 3 of them that were having a double specificity between the alcohol and the substrate. In the overall of all these mutants we generated, and after the screening, we selected 27 of them that we have immobilized for screening using the original assay and coming back to the original condition where the industrial enzyme will be applied. So what we found from that, when we compare to Novozyme 435, we found 2 mutants that were having high specificity for the alcohol group in the original condition that will be industrial 1. No recognition for impurities within 4 mutants, and also one that was having an improved rate mutant. Unfortunately, after 1 round of evolution, all these mutants were independent. Here, you've got a representation of the conversion rate for 2 of the mutants that were recognizing specifically the alcohol group. The candidate referent that was here, and in the y-axis, you've got a percentage of conversion, but using this time the non-specific alcohol group, meaning the wrong alcohol, the wrong esterification we don't want to avoid. As you can see with the Novozyme 435, you've got quite a high rate of this non-specific alcohol group recognition, and when you test with the new mutants, the rate is near 0. So the next step of this project will be to combine individual mutations and or perform a new evocyte library and combining the result of both library. So that's still a program ongoing. But because I wanted to show you an example of where evo sites allow us to generate sufficient performances to go straight to the industrialization, that will be the case with this example where for a squalene open cyclase, we look at the formation of foam blocks. And after 1 round of evolution, we managed to identify 3 variants with improved activity factor from 1 to 3 times. And after optimization of the condition of culture and the reactions, 1 variant allows us to improve by 10 times the activity. So this mutant has been moved forward for industrialization, and it was a project run for Givaudan, and you can find all the detail in this article. I thank you for the attention. I would like to acknowledge all the people that have been working on this project: Céline Erignac, Pascal Offray, Olivier Bonzon, Christophe Hillman, and Juliette Martin. Thank you.